Welcome to another EC&M Tech Talks. Energy storage systems. We have 5 topics that we're going to talk about today when it comes to energy storage systems. The first thing we want to do is we want to go over maybe the definition, and then we're going to get into the different types of energy storage systems and really the ones that we end up installing and working on and maintaining mostly. One of the big components of energy storage systems is batteries. So the third topic we're going to talk about is battery safety, obviously a huge issue. Then we want to get into the energy storage systems that we typically install, and we want to take a look at how they work. So we'll go through a one-line diagram and we'll talk about some of the basics then as we jump into Article 706, which is energy storage system requirements. So let's jump in and let's first talk a little bit about energy storage systems. Now there is a definition in Article 100 of the NEC for energy storage systems. Let's just talk about plain and simple here. I take and I make electricity. I don't need it all right now. Let's say I make it from a wind generator or from a solar photovoltaic system. I take that energy and I store it. I convert it into another form of energy. I can convert that energy into kinetic energy. I can convert it into a chemical energy, which is going to be the most common we're going to see and that we're going to talk about. And then when I'm ready and I need that electricity, I can take it out of that storage system and I can convert that, say, that chemical energy back into electrical energy. So if we look in Article 100, there is a definition, and I'm using the 2023 NEC, as usual, the most current edition. It says one or more devices installed as a system, an energy storage system is, capable of storing energy and providing electrical energy into the premises wiring system or an electric power production and distribution network. We'll have to talk about what that is and the difference between primary power. There are lots of definitions relating to energy storage, energy management even, of course photovoltaic systems in Article 690 and so on and so forth, all found in Article 100 of the NEC. Those definitions, as we get into Article 706, I think, as we run into them, we'll go ahead and talk about them then. Okay? So anyway, energy storage systems. We take in some type of some energy from the sun or whatever it is, and the wind, and then we're going to take and store it to when we need it, convert it back to electrical energy, and put it back in to our system. So what about the different types? Well, if we go to one of the government websites on energy, we find that about 95% of our stored electrical energy in the United States come from pumped storage systems. And these are kinetic type storage systems, meaning that, for instance, I have one actually not far from my home. We have a big lake up on top of the mountain, and during the day when electricity is in most need, the water flows down the mountain, comes down, goes into a dam, goes through some turbines. The turbines turn to a generator. The generator produces electricity, of course, which goes out onto the grid to serve the public. And then the water goes into a lake at the bottom of the mountain. Now, at night, when less electricity is needed by the customers, we now take and turn those generators into motors, and we use those turbines as pumps, and we pump that water back up to that lake at the top of the mountain, ready for the next day. Now that accounts, the government says, for about 95% of our stored energy. If we're going to install something like that or maintain it, we probably work for the utility, and it's a big industrial project. What we want to talk about is more what we find in Article 706 of the NEC on energy storage systems. Now, there are other types of ways to store electrical energy. We certainly do it with capacitors and all types of systems. We could use compressed air, but probably the most common types of energy storage systems are going to be batteries. So Article 706 of the NEC is going to talk about batteries. It's going to talk about a specific type of battery called a flow battery. That we'll mention that and see where that might apply. And something else that does produce kinetic energy for us, and we take that kinetic energy, turn it back into electrical, and that's the flywheel system. Not nearly as common as batteries. But anyway, we'll talk about those different systems in Article 706. Next topic, let's jump and take a quick look at battery safety, since I said most of our discussion is going to be around battery installation and maintenance. Now, batteries. There was the lead acid storage battery that's still widely in use today. It's used a lot for standby power systems where we have a UPS. And so if you had a large facility, you may have lead acid storage batteries. High maintenance items, lots of acid, unfortunately, to have to mess with, and lots of maintenance anyway involved with those as far as routine testing and visual inspections and measurement of electrolyte levels and so forth, and temperatures and adding water to the battery and all of that. And, you know, sometimes people will ask, well, what PPE do I wear when I work on a battery? Do I wear my electrical PPE, my rubber gloves and leather protectors, and my, Category 2 face shield or whatever it is? Or do I wear my rubber apron and rubber gloves for working on the battery? Well, I think you'll find the general consensus is take a look and see what the most prevalent or what the most relevant danger is to you at any point in time. If you're going to go work and do maintenance on a lead acid battery, it's probably more important to protect yourself from the acid. So you would want to wear the rubber apron and the chemical rubber gloves and so forth, and the face shield and safety glasses, whatever your requirements are to protect yourself. Now that's another whole set of requirements. There are IEEE standards on lead acid storage batteries. If you have those, take a look at those. Also in the NEC, there's Article, I believe it's 480, that covers the installation of those stationary battery systems like we use in our UPS systems. But when it comes to energy storage systems, the most popular battery right now is the lithium-ion battery. And why is that? Because for a given size of battery cell with lithium-ion, I can put a lot more energy into that cell than I can, say, with the older lead-acid types. So that's a good deal. I can put a lot of energy in a small area. Now, the drawback to the lithium-ion battery, I can put a lot of energy into a small area. So inside the lithium-ion battery, I can create a lot of heat. And when that heat, if it, of course, results in fire and explosion, I can end up with toxic vapors and fumes given off, metals burn, and so forth. A lot of heat produced. The NFPA 855 standard is the standard for the installation of stationary energy storage systems. It has a lot of information. But let me review a little bit of the information with you on battery safety from the NFPA 855 standard then. First of all, the standard itself, it says it applies to the design, construction, installation, commissioning, operation, maintenance, and decommissioning of stationary energy storage systems. Covers everything to do with energy storage systems, right? Now, it includes both mobile and portable. Article 706 of the NEC is going to talk about just our stationary energy storage systems, what we typically get involved with. When it comes to battery safety, the 855 standard then breaks it down into 4 hazards for us. Fire explosion that I just mentioned to you. There are chemical hazards associated with the release of all that energy, in the fire and explosion. And there are toxic vapors and fumes. We can get liquid on our bodies and so forth that can give us burns. Not a good situation. The electrical hazards are already what we know about. Shock and arc flash, right? Now, the thing we have to remember about a battery cell is we can never shut it off. In the energy storage systems, we're required to have disconnects on the batteries, but that doesn't turn the battery off, does it? There's no switch on the battery cell that I can go from off to on or anything like that. So it's always energized. In fact, even when I'm replacing that battery cell, because it's gone bad. It's no good anymore. It's not producing enough power. There's still a lot of energy left in it, enough to shock or cause an arc flash. You know, just a simple example, you would never go out to your vehicle, your car, your truck or whatever, and get a big old wrench and put it right across that positive and negative terminal on those battery cells. That would be crazy, wouldn't it? Don't ever do that, okay? We know that there's a big release of energy there, and there's a lot of heat. And if that battery were to blow up, it would be really dangerous. We could, of course, get covered with acid and burned and so forth from the heat and the acid and all of that. So anyway, there are electrical hazards. In addition to the shock and arc flash, we want to make sure that we use the proper tools when we ever work on one of these battery cells or batteries in general. We don't ever want a tool that is uninsulated for enough length that could get across a positive and a negative terminal. So we usually use insulated, non-sparking type tools. Also, gases are given off. We call it off gases, just during the normal operation of different types of battery cells. And those gases can be explosive, they can be bad for our lungs, and so on and so forth. OSHA and NIOSH give us the limits for the maximum amount of exposure that we can have to different vapors and gases and so forth. And we want to pay attention to those, because if we inhale those gases and vapors today, we don't think anything about it. But it's months, years later before we start to see the effects. And then it's too late to do anything about it, and nothing can be reversed. So pay attention when it comes to electrical safety and batteries, okay? One more thing I'll mention, a physical hazard too. We're going to talk about flywheels in Article 706. Flywheels, so I have this typically big three-phase motor turning this big, humongous flywheel that's made of some type of metal, and it's maybe, I don't know, 3, 4, 5 feet in diameter, whatever it is, particular application, maybe so thick or something like that. And it just sits there and spins, usually on a synchronous motor, and just turns at that synchronous speed or whatever. And in the event there's a loss of power, then that flywheel starts to drive the motor as a generator and produces electricity, of course, that goes back into the system. So some of those can produce power, usable power for maybe up to 15 minutes while that generator spins down. We see them a lot in UPS systems maybe. Not a whole lot, I'll say, but quite often we'll see them in UPS systems where we need time for that standby emergency generator to come up to speed and start delivering power. And remember, depending on the type of power system it is, whether it's an emergency or legally required standby system, an emergency system, that generator has to start and come up to speed within 10 seconds. So if we want to keep power into our facility for those usually 5 to 6 to 7 seconds before the generator's online, we need something to do that, and the flywheel can, of course, do that. Also, it can do it in the legally required standby systems. It can go for up to 1 minute in those systems. So anyway, it depends on the application for what we need. So be careful of batteries. Be careful of the physical hazards around flywheels. Usually they are well guarded. We can't get to them unless we shut the equipment down and so forth. So anyway, safety first, right? The next thing we want to do is let's take a look at how this system works, okay? And so we're going to look at a one-line diagram. Now, this one-line diagram shows a typical energy storage system. This is courtesy of We Energies. So they're a large energy company in Wisconsin. They serve about a little over 2 million different customers. But anyway, they provide to their customers free of charge, as many utilities do, various one-line diagrams to say, hey, if you're going to install one of these systems and, work with us and so forth, here's what you need to do. So let's take a look then at the energy storage system one-line diagram, a generic one. Give us an idea of what we're talking about. So let's start over here on the right-hand side. We're going to take a look, first of all, it says solar panels. So this would be solar panels. Let's say this is a dwelling unit, commercial installation, something like that. And so these are probably mounted up on a rooftop. So the solar panels are connected up on the rooftop and strings and so forth, and are going to provide DC power. Well, of course, I need alternating current power, so I'm going to have to go through an inverter in order to produce the AC power, change the DC into AC. That's what the inverter does for us. Now, also I have a battery down here on the lower left, and of course that battery, what it does for a living, it stores electrical energy. And when we discharge it, it takes that electrical energy out and puts it back into the inverter where it's converted into or inverted into alternating AC current and goes into our system. Coming out of the inverter, I can go in one of two directions. If I go up straight, I can up to the top, I see something called islanding AC connection. So that's called the island mode. Now that's defined in NEC. It talks about it primarily probably in solar photovoltaic systems and so on. But anyway, it's defined in Article 100. And Article 100 tells us that when we're in the island mode, we're just supplying, for instance, and here's the example. This is a 120 volt battery backup loads panel over here on the right hand side. And that's all that's being supplied by the inverter in this case. So if I were to lose power in my system, the inverter would, through the battery discharge, would convert the DC into AC and then supply this panel board over on the right-hand side. I would not be connected to the utility if I were just in the island mode. However, over on the left-hand side out of the inverter, we can see the power goes up, goes through a fuse disconnect. It may or may not be fused, but we're going to go through a disconnect, and that disconnect is going to go up to my, in this case, it says optional non-battery 12240 panel, but look what it's connected to. It's connected over here to an export meter, and then goes back to the utility, doesn't it? So this is my utility service, or what my definitions in Article 100 are going to call primary power. If I have a system on site where I'm producing my own power, and so it's called a network power production system. Now the inverter, and because that brings us back to the inverter, this inverter is called an interactive inverter. What we mean by interactive inverter, that I can parallel it, and the definition once again in Article 100, but I can parallel it with other power sources, be it either the primary power source from the utility or the network power production the power production network, I should say, at my own facility. So that is what we talk about when you hear that term interactive inverter. I can parallel its AC output with other sources. And with that disconnect closed, that is just what we're doing. And with that disconnect closed, that is just what we're doing with this interactive inverter. We would be supplying this panel board in parallel with the utility. We go through an export meter, so maybe we can charge the utility, for power we're putting back onto the grid, and or we can operate in parallel. And in the case the utility power is lost, the interactive inverter would continue to supply AC power up to my panel board. So that's a little basic of how these systems work, these energy storage systems. All these components must be listed. The energy storage system, we're going to see in Article 706, is required to be listed, and it's required to have a nameplate on it. That nameplate is going to be important to us because we can go to that nameplate and we can pull information off of that nameplate to do things like, let's say size conductors, determine the ampacity requirements for the conductors that we need, and so on. The next topic, let's jump into Article 706 itself and go through some of the highlights of Article 706. Article 706 is on energy storage systems. 706.1 gives us the scope, of course, and it says this article applies to all energy storage systems having a capacity greater than 1 kilowatt per hour. It may be standalone or interactive. Oh, we just talked about that, huh? Good example maybe of a standalone system. You build a cabin way out in the middle of nowhere somewhere, not close to any electricity, and you need your own energy storage system at that location. It's a standalone system, where, as we've already talked about, if I parallel with the grid, it's called an interactive type system then. Okay? And And it says, I can either parallel with the interactive or other electric power production sources if I have them at my facility. Now, these systems are primarily intended to store and provide energy during normal operating conditions then. Well, we talked about that. We convert electrical energy into some other form of energy, then we convert it back into electrical energy again. In Article 706, there are 6 different parts that we have to pay attention to. We're going to run through those parts and we'll see what type of information is in them and what we need to be able to pull out of them. Part 1 is general information. Part 2 is disconnecting means. Part 3 is going to be installation requirements. Part 4 is on the circuit requirements, and that's where we also get into ampacities of conductors. Part 5 is a special type of battery, a flow battery. You probably don't have any flow batteries, I'm guessing. Flow batteries use a liquid electrolyte. The electrolyte, I have a positive electrolyte and a negative electrolyte, and I store them in tanks. And then there's a grid in between the 2 tanks, and that's where the electricity is produced. So they're a little bit different systems. And then we have other energy storage technologies is Part 6. Right now, the only thing that's addressed in Part 6 is the flywheel. And there's not a whole lot of information on it, but there's certainly some good information there. I think it's probably titled Other Energy Storage Technologies because there are others coming online, obviously. A lot of research going on in the energy storage system area, changing all the time, new batteries, new battery systems, new storage technologies, and so forth. So anyway, we're just going to see more and more of that over the years. Article 706 first appeared in the National Electrical Code in 2017. And of course, it's going to continue to grow and continue to grow as our distribution systems change, don't they? Okay? So now let's jump into Article 706 a little bit more and take a look at some of the specific requirements. So once again, using the 2023 National Electrical Code, Article 706, if you have the code book, it starts on page 643. So Part 1 is general information, and we've already covered that really as to what it applies to in the scope. Only qualified people in Section .3, it tells us, can install and maintain these systems. We kind of already know that, don't we? But anyway, we have to be qualified persons. Definition for the qualified person back in Article 100 again, as well as like NFPA 70E. There's required to be a nameplate it talks about in 706.4, and so for the energy storage system. So we can look on that nameplate because you think about it, what are we interested in? We're interested in input voltages, output voltages. We're interested in current ratings as well because we can use that current rating in order to size the ampacity of the conductors. So nameplates are required to be there, and 706.4 then lists all the requirements on the nameplate. We talked about it all has to be listed, and 706.7 talks about I have to not only maintain my energy storage system to keep it safe, but I also have to commission it. Now this doesn't apply to 1 and 2 family dwellings, but I have to go through a commissioning process. NFPA, that NFPA 855 once again, gives me information on how to commission these energy storage systems, as well as other resources. Part 2 gets into the disconnecting means. We do have to have that disconnect for the entire energy storage system. We're also required to have a battery disconnect down here. Now the battery disconnect, that's interesting because remember, even though I have the battery disconnect, it doesn't turn the battery off. I'm also going to have overcurrent protection for the output of that battery. But once again, that's not going to turn the battery off, is it? It's going to remain energized. The same is true over here on my solar panels. I can't just turn off a solar panel only if the sun goes down. But if the fire department shows up, even if it's at night, what's the first thing they're going to do? One of the first things, they're going to put up those big lights and shine where? Right on my building or structure, and now I'm going to start producing power out of my solar panels. So I'm required to have a rapid shutdown to de-energize the wiring coming off of those solar panels. Once again, all of that information is in Article 690 on our PV photovoltaic systems. Take a look at those specific disconnect requirements. There are markings that are required to be on the different disconnects. for example, on the batteries and so forth. So anyway, and think about it, it's all just as I call my electrical common sense for safety, right? Sure, I should have some type of placards that are in accordance with what's in Article 110 about marking requirements and all of that, and have that information on those labels. So I always think of it in an emergency situation when I run up there. I want to know what the voltage is. I'm going to shut that disconnect off. I want to know how it's tied into my system and so forth. That general disconnect for the entire ESS system up here at the near the top, that disconnect is required to be either part of the energy storage system, or it must be within inside of the energy storage system and within 10 feet, not the 50 feet you're thinking of, but within 10 feet and within inside of that energy storage system. If not, then if I'm not part of the energy storage system or within that 10 feet and then within inside of, then my disconnect has to be capable of being locked in the open position. So anyway, pay particular attention to all of your disconnect requirements. They're very specific when they come to energy storage systems. Part 3 talks about the installation requirements. One of the big issues is ventilation, and we've already talked about battery safety. So we have to have proper ventilation. Now, where do you find all this information? Manufacturer's instructions, right? So pay attention to manufacturer's instructions. Also, when I think of installing this ESS, don't forget 110.26 also applies for my working space about my energy storage system as well. And being able to open and close your doors a full 90 degrees and so on and so forth. Adequate illumination and all those things may be a requirement. So pay attention to 110.26 as well. Part 4 is on circuit requirements. 706.30 is divided up into different subsections, and it talks about circuit sizing and ampacity of conductors. So in subsection A of 760.30, it talks about circuit sizing and going down the nameplate and determining the size of your energy storage system, your ampacity requirements then. And then subsection B goes through and talks about those conductors. And your ampacity of those conductors have to meet one of two requirements. They have to, whatever the information you just got off of the nameplate, as far as the current rating of your energy storage system, of course your conductors must be large enough to support that, or the ampacity of those conductors must meet rating requirements of the overcurrent protective device for your system then. Overcurrent protective device itself is covered in 706.31b. Overcurrent protection is covered in 706.31. Now, Part 5 is on flow batteries. I already talked a little bit about what the flow battery is, and so it's placed in Article 706, and it's a fairly short part. It's only about 4 or 5 different sections. So anyway, if you get involved in installing or maintaining flow batteries, you'd want to take a look at that particular part. And then Part 6 is on other energy storage technologies, and that's where the flywheel is included. A couple of the interesting requirements on these flywheel systems. It says it's got to meet 4 requirements. Can't be used in 1 or 2 family dwellings. Shall be provided with bearing monitoring and controls that can identify bearing wear or damage to avoid catastrophic failure. Well, you think about that. Here I'm spinning this big flywheel 24/7, big heavy flywheel. Should that motor fail, and that flywheel come loose or start coming apart or whatever, could be pretty catastrophic, so we wouldn't want that to happen. So we're required to have monitoring systems there for safety. The flywheel storage system shall be provided with a containment means to contain moving parts that could break from the system upon catastrophic failure. Probably a good idea. The spin down time of the flywheel energy storage system shall be provided in the maintenance documentation. Righty? So anyway, and that's it on Article 706. Now keep in mind there are plenty of other articles that tie in anytime we're going to install or maintain an energy storage system. Take a look at NFPA 855. That's an excellent document on the installation of these energy storage systems. And so, till next time, work safely, especially around batteries and energy storage systems. We'll see you at the next Tech Talk.